Great, good morning. Good to see you all. My name is Sebastian Schlecht, and I'm presenting today a work which is called Physical Modeling Using Recurrent Neural Networks with Fast Convolutional Layers. So this is kind of a mouthful, but I'll explain hopefully well what this is about. I'm very happy about kind of the context I have here in the session. So you'll see very, very familiar things again in this talk, but I try to recontextualize those in the world of neural network. So this is joint work together with Julian and Rudolf Rabenstein and Maximilian Schäfer. So maybe as a first comment, I would like to state a bit my attitude towards that topic. So I'm coming from a signal processing physical modeling background, and I'm fairly new to deep learning. So there's kind of a mixture of skepticism and kind of magical awe kind of seeing there. And the question is, well, we're trying to kind of go towards in this work is, we'll have all this knowledge about physical modeling. Is it kind of worthwhile bringing this into neural networks? So very much in the spirit of what Gayatri showed yesterday in the keynote. So does this kind of just make us feel clever, or is this actually kind of useful? Spoiler alert, I'm not answering this question conclusively, but hopefully I show kind of an experiment towards that. So this is the task we're looking at, so a generative physical modeling with neural networks. So we're taking a spatial temporal data, a string, and have a neural network, and then we would like to predict the next time step. From the previous time step, we can do this over and over again, so you kind of get the full time evolution from an initial condition. Here in the bottom left, you see kind of just the very generic version of a PDE. Just for notation, U is again the state. That seems to be kind of a common thing. That's nice. Then X is space, T is time, and G is then the thing the neural network should learn, so the spatial temporal dynamics. Now, so the naive solution to that would be that we'll just say that whatever we have at the time step is just a vector of data, and we just predict the next vector of data. So this could be, I just wrote here fully connected network, but you can just choose your favorite one. But essentially kind of what it does is, yes, it preserves the temporal structure because we're going from time step to time step, so this stays ordered. But the spatial data, you could kind of essentially permute the input data and the output data, and you probably would get exactly the same training and the same results. So that's kind of what I mean with kind of ignoring the spatial structure. And now I'll digress a little bit to somehow motivate what might be a little bit of a clever way to do that. So that's something you've already seen now. And so that's a very classical way to represent the motion of a string as a superposition here of modes. So we have 3 of those as a standing wave, and then you can also represent this again as a multiplication of spatial modes, which are invariant over time, and temporal modes, which are have no spatial component. And these spatial modes are then, well, in this very ideal case, they look like trigonometric functions, sinusoids, and these temporal modes are exponentially decaying sines. So that's what you typically get in a linear system. And this is a bit more elaborate in the paper, can be kind of then formalized more broadly with functional transformation methods. So we'll just add a bit of kind of symbols. So we have K for the spatial modes, U bar for the temporal modes. And essentially, this PDE gets converted into a state space representation. So here on the bottom, you see here we have the input data, so U, spatial temporal dependency, and then we have a transform with the spatial modes into these decoupled states. And on the top you see the time stepping, so going from, I changed, by the way, from T to K, just because it's discrete. So we're moving from one time step into the next, by this operator. And the important thing is, in this ideal case, A would be a diagonal matrix. So every mode kind of evolves by itself. Now, can we kind of use this? And I guess a bit the thing we're trying here is kind of squeeze your eye and kind of imagine a not so ideal situation and kind of what would be still a good way to represent this. And so the thing we're using here is that, well, that looks like sinusoids, so let's use a Fourier basis for it. That might be a good representation to get something sparse. And then here for the temporal modes, maybe these are not exactly exponentially decaying sinusoids, but something which is easily represented with a tiny RNN, or with a kind of a full battery of tiny RNNs. And combining these two ideas gives the Fourier neural operator. So this is a term which was introduced 2 years ago, kind of more from the physics community. So they were looking at more fluid dynamic things. And, well, we were interested in, does this bring anything to our case? So this is really kind of the full concept of the paper. So if anything is important here, and then is this type of representation bringing anything to this task? And the rest, I'll tell you a bit more about kind of the technicalities and what's actually kind of how we create these structures and how we perform the experiment. So the first structure is here the Fourier recurrent neural network. So we have now age as the hidden state, time index k. We're trying to predict kind of the next step here by going through a bunch of cells. And here is more detail on one of those. It has the weighted skip connection, a ReLU, so very standard things. And now the interesting bit is in S. And here's the definition of S, the fast convolution layer. So we input here the previous hidden state, apply an FFT, multiply it with some diagonal weights, do some bias because that's what you do in machine learning, and then you do an IFFT. The FFT is a bit more, it can have some extra things, zero padding, it cuts or it just keeps the real valued parts for efficiency, but in the end you see that's more or less a circular convolution. If you're familiar with CNNs, then you might see that this is a pretty big convolutional layer. So the receptive field is actually kind of the whole spatial domain. So depending on the resolution you have on your string, you're doing an FFT across the whole string, or later on also on the whole plate. Yeah, so this may be also the reason why using kind of a fast convolution might be here much more beneficial. Good. You can apply then this type of change to all kinds of structures. We just take here another famous one, the gated recurrent unit, and essentially you're just replacing all of what you have typically as linear layers with these fast convolutional layers. Then there's one extra bit which seemed beneficial, is the soft state matching. So we have one extra kind of mechanic to transform the physical states into the hidden states. So we have these extra maps M in, and we do the thing after the prediction in the hidden state back to the physical states. So this is one more way to well, have a transform between these domains. Okay, so going to the training, just a little bit of details on this. Most of this is really very, very basic type of RNN training. So the simulation comes from mostly FDM models. We have these regular spatial temporal grids, so nothing fancy there. So we have a tensor of m+1 dimensions, depending on the dimensions of your space. Maybe one interesting bit is here on the initial conditions, we have kind of a mixture between kind of local excitations with impulses and plugs, or random values across the whole domain. So here's an example of those. So either we do have kind of these local excitations, or kind of start with a noisy signal. And then, just because I showed this type of plot in the next few slides, so here we have the time evolution then. So here you have the space, and time goes from top to bottom. So you see kind of in the plug case, the infamous traveling waves here. Good, so what are the results? Let's start with something simple, so a linear lossy dispersive string. Here on the left-hand side you see the time evolution. We have 4 cases now. The one is on the most right is the ground truth. Then we have the reference, which is just a Fourier neural operator in a forward manner, so not recursive. And then we have the simple RNN structure and the GRU. And then here in the same way, just from bottom to top. And the right one is also an animation. So you see, you can, the ground truth has kind of a nice long-term time evolution, rings for some time. You see that the reference kind of breaks down very quickly. Actually, I indicated also here on the left-hand side the training duration. So that's the time bit we are training on. And so the reference doesn't generalize much over it. The RNN structure is kind of okay. It's continuous ringing, but it's somehow erratic. But the GRU is fairly similar to what we have on the ground truth. And here's one other way to look at this. So you can kind of take the resulting data and do an eigenvalue analysis. So you're basically kind of enforcing a linear operator from one time step to the next, and run an eigenvalue decomposition on it. Here, these purple squares are the ground truths, and maybe most interesting are these blue crosses. I hope you can somehow see them. So they line up fairly well for the low frequencies, but for the high frequencies, they seem overdamped. And well, that might be a bigger pattern, that spectral bias, that higher frequencies might be harder to learn in general. Okay, so a little bit more sophisticated example with a tension-modulated string. So you're kind of overstretching your string, so you have some extra nonlinearities. The results kind of have a similar tendency, that the GRU is fairly close to the ground truth. The RNN is not doing terrible, the reference does. And here, one last bit on a 2D example. Just a 2D wave equation. For some magical reason, this pattern is now broken, and the reference is suddenly the best one. That's a disappointment, but, well, that's future work, I guess. So here the overall results. So GRUs are kind of good for 1D and 2D, but this is not a scientific conclusion, please. So, okay, so let's go to the actual conclusions. Well, these Fourier neural operator seem to be like a viable physical modeling tool to me. They're applicable to musical synthesis, so you can do kind of longer time series predictions with those. And this modal interpretability is something we really like to kind of exploit and study in future work, and to see how much this actually kind of represents something we can use and add more theory. For example, from FDN. And other future works is kind of looking at more challenging cases with nonlinear problems and more complex geometries. If you're interested in, have a look at the code and the sound examples. Everything is public, and here's also a QR code for that. So thanks a lot for your attention.
Thanks for the talk. That was really, really interesting. So I suppose there will be a few questions from the audience. No takers? Yes.
Hi, great talk. I was wondering if you had looked at doing any like frequency domain preemphasis to combat the overdamping that you saw at high frequencies?
No, we haven't done that. That's of course, yeah, of course you can do that. Somehow it feels a bit of a trick at that, because we're kind of not looking that much at performance at that moment. I'm more happy to see kind of a clean, kind of analyzable kind of system than kind of trying to squeeze out kind of the best performance at that moment. But that would be, of course, kind of skewing the loss function or towards kind of the critical parts. Yeah.
Thank you.
Hi. I think I missed something. Oh, it's in the center. Hi. I think I missed something. You mentioned that like the receptive field, when you're thinking of spatial modes, is the entire string. But I think you said that kind of the receptive field of a normal like time-stepping operator is just like some local area. And does that idea ever come back in here, or are you always considering like this Fourier neural operator across the entire string?
I think the only thing I wanted to tell, I think in CNNs you often have very kind of short kernels, right? So I don't know, a handful or a bit more, but this could be kind of thousands and thousands of samples you're kind of looking at. So that was the point I tried to make. Maybe you can ask your question.
Yeah, I guess my question was: is the receptive field of these always the entire string, like of S here?
Yeah, I think from our point of view, I think I'm just saying that we're kind of transforming the entire string in one operation. We're not kind of doing kind of local bits of the string. So that would be the alternative, that you kind of just maybe if you're thinking more from an FDTD domain, that you have kind of a more local operator, you could also do that, right? Kind of do snippets of the string and work on that.
Thanks. Can I ask one other quick question? If you go to the first slide where you show the 4 comparisons between the simulations, like the four time versus space versus color, the comparison between the reference and the FN and the FGRU, maybe like 2 more slides forward.
Forward. Okay.
Okay, maybe one more. Yeah, in the reference, is there a zigzag? Does the blue traveling wave on like the 3rd panel from the left, does it change direction near the end?
Here?
Yeah.
Yeah, that's not good, right?
Yeah, that's scary looking. Okay. Thank you.
Yeah, that really doesn't seem to work at all, which is, I don't know, it bothers me a bit that it's so bad, because we're still kind of giving the same kind of structural prior to this. So actually what I was kind of, when I created these slides, I was looking for that it would have been nice to really destroy the structural prior and see kind of the difference here. In this case, really the reference still has its just a feed-forward structure. So it really, I think the trouble it has, it doesn't compensate for the error it creates. So that's with the RNN and with the backpropagation through time, that you're kind of compensating for your modeling error or prediction error over time. So it stabilizes it automatically. The reference doesn't do that. Yeah.
Interesting. Thanks.